We're working on page 200, no, not 200, 205, numbers 81 to 90 all. All right, catch the mistake. Number 81. So we have the functions f of x and g of x, and we're asked to divide g of f of x and then state the domain. So we have this function, and we state the domain is everything. Why is that incorrect? Negative 2 is not part of f, so it can't be part of g of f, even though it divided out. It ends up that's just a hole in the original graph. So x equals negative 2 is not part of the domain. So it should be from negative infinity to negative 2, union with 2 to negative 2 to infinity, or I would accept all real numbers if x is not allowed to be negative 2. Okay, 82. So we have f divided by g. So that simplifies down to x 1 over x minus 2, and it states the domain is all real numbers, but x is not allowed to be 2. Why is that incorrect? So why is this domain not accurate? Certainly we can't plug 2 in there, but why is that domain not right? Anybody get this one? Negative 2 is also not part of the domain. If I plug negative 2 in there, nope, in there, so that canceled that, but negative 2 is not part of the function f over g, because then the denominator would be 0. So if you plugged in 2, you'd get 4 over 0 plus times 4. That's a problem. If you plug in negative 2, you get 0 over 4 times 0. So this is the function. That's the function. And we simplify it down to 1 over x minus 2. Now, those two graphs are identical in every way except one. What's the difference between the two? This graph is going to have an asymptote at x equals 2. So over at 2, we have a vertical asymptote. So I'm going to imagine the graph looks like this and like that. That is the graph of this one. How is this graph different? Do you remember what happens when you cancel factors? Well, we know that x is not allowed to be 2 and negative 2, and 2 is an asymptote, but negative 2 is a hole. So those two graphs are identical, except the second one, the hole has been plugged. That's what happens when you cancel factors. So over here at negative 2, there should be a hole. So you're perfectly welcome to simplify rational expressions. But if you cancel x's, you need to remember that that ends up plugging a hole that should be there. So this is the correct graph, or you could graph this with a hole at x equals negative 2. Okay, next page. 83, f of g. So f of g is f of x times g of x, simplifies down to this. What's the mistake? Right. F of g is not the same thing as f times g. F times g can be written f of x times g of x. But f of g, that open circle, is actually f of g of x. So the issue is right here. That is not a multiplication symbol, it's a composition symbol. Okay, number 84. F of x minus g of x. I don't remember what the functions were. They were x plus 2 and x squared minus 4. So I take f of x and g of x and subtract them, and I end up with that. What's the mistake? Right, they didn't distribute the negative. So this is g of x, in which case the negative should distribute through, turning that into a plus 4, which would give you a slightly different version. Okay, 85. F plus g of 2. So here's f of x, here's g of x. We're multiplying that by 2, so we simplify f plus g, and then we distribute the 2. What's the mistake? That's not a multiplication problem. It's saying evaluate f plus g at 2. So you have two ways to do it. Either you take this and simplify it down to that, and then plug into, so you'd stick a 2 there and stick a 2 there, or you do f of 2 and add that to g of 2. So you'd plug 2 in there and plug 2 in there and add the two values together. Okay, 86. Given the function f of x and g of x, find f of g and state the domain. So f of g, we're going to stick g inside of f, so we take x minus 3, the square root of x minus 3, plug it into x squared. So we stick this in there, the squared and the square root cancel. We're left with x minus 3 plus 7. So x minus 3 plus 7 is x minus 4. The domain would be all real numbers. What's the mistake? So this is just a simple addition mistake. Negative 3 plus 7, it should be x plus 4. Okay. Bring that back up. Okay, true or false? Number 87. When adding, subtracting, multiplying, or dividing two functions, the domain of the resulting function is the union of the domain of the individual functions. Why? If we go back, they stated it. So if you look on page 202, talking about composition of functions, the domain restrictions cannot always be determined simply by inspecting the final form of f of g of x. So you can't necessarily look at the end and find the domain. We did that with that hole that was plugged. Rather, the domain of the composite function is a subset of the domain of g of x. What that means is, since we started with g of x is as big as the domain could be. So if g of x had a restricted domain, that restriction is going to follow it through, but the domain of f can further restrict the domain. So union is the wrong word. Intersection, I think, is the word it looks for. Values of x must be eliminated if their corresponding values of g of x are not in the domain of f. So intersection is the word we're looking for, not union. Okay. 88. For any function f and g, f of g of x is equal to g of f of x for all values of x that are in the domain of both f and g. Oh, you guys couldn't even see that, sorry. So, Is f of g of x equal to g of f of x? No, in fact, it's only true in one case. When are those two compositions the same? So y equals x is a case where that would be true, because y equals x is its own inverse. This is only true when f of x is equal to g inverse of x. If they are inverses, then that's true. It's like saying, well, that's a bad example. Function composition is a little bit strange. So if you take f of g of x and g of f of x and they're the same, that means that they're inverses of each other, because when you compose them, f of g of x is going to equal y equals x. Does that make sense? So that one would be false. 89. For any functions f of g exists for all values of x that are in the domain of g of x, provided that the range of g is a subset of the domain of f. Wow, that was tough. So let's do this. This is f, and we're drawing lines across here. Then we have g. So it says the composite function f of g of x. I'm going to write that as f of g of x. So we're allowed to plug g into f as long as, I can't read that at the moment, provided that the range of g is a subset of the domain of f. So this works as long as these values all show up over here. Is that true? So if we're going to follow, we're going to take x and plug it into g, so that will create this list, which creates that list. And as long as these all show up in this list, we can keep going and create the f function. True or false? True. That is the requirement. The answers for g have to be able to be plugged into f. If they can't be plugged in, there's nowhere to put them, and the function doesn't exist. What if only one of them works? Is that still a function? Yeah, you still have one to plug in somewhere. It's going to have a domain of one number, but it still works. 90. The domain of a composite function can be found by inspection without knowledge of the domain of the individual functions. Can you look at the end version of a composite function and determine what the domain is? No, you have to know what the original functions were, because each original function can have domain restrictions. Okay, hand that in.